got? Morning, everybody. We got some folks joining us from home from cohort A because I did some stuff yesterday that I think should go by a little bit faster with you today because you did that classwork at home. But I want to look at homework 2.1b first and then the classwork from yesterday. Folks at home, just make sure that you check yourself in on Infinite Campus. But feel free to tune me out for a little bit while I go over the 2.1b homework. And then I'm going to look at the classwork from yesterday, but we'll talk about discriminant and we'll talk about vertex form. Homework 2.1b solutions. There we go. Okay. So real quick, take a look, see how you did. I want to give you a chance to look through this, make sure you get it. Like, I want to be done with 2.1 today for sure, but there's a couple things that came up in this homework, mostly with questions 4 and 5, and then on the classwork that I assigned yesterday that I just want to make sure that we're cool with. And then it'll kind of give you a choice with what you want to do when questions like 4 or 5 come up that just aren't factorable in a way that we would like. So good. Okay, scrolling to. Obviously, things get a little bit trickier when you've got that leading coefficient. That's just different than 1. Messes up our vertex a little bit, but fractions only there because that decimal goes on forever, right? Negative 2.6666666, and whatever 49 thirds is a lot. But it was factorable, which was nice, and there's factoring by grouping. You could use a box. Either one's cool. I'm happy either way. Factoring by grouping is just nice to know. The order here doesn't matter. Right, but what we like to do is we like to put that largest leading coefficient first. Whatever the factor is that has the biggest leading coefficient, let's make that the first. And then when we write a solution set, usually we go from left to right on the number line. Good. Okay, nice. Making me happy. Number 3, also factorable, pretty nice. This one you could have used decimals for the vertex. That would have been fine. Negative 2.25. And then negative 0.125. Now, if you're going to use a decimal and it's 0 point something, use the 0. Don't just put negative 0.125 because that decimal sometimes gets lost. And we don't want to lose that. So I like the leading 0 there if you had to do the negative 1/8. Okay, and then 2 and 2.5 are going to be your x-intercepts. And then when I was looking at 4 and 5, I saw that there was just some issues that we ran into. So I want to make sure that we're okay with the kind of things you should expect when things aren't factorable, when things don't have really nice x-intercepts because of that, right? If a function's not factorable, some quadratic isn't factorable, doesn't mean it doesn't have x-intercepts. It just means that they might be just not so nice, right? They might be irrational. And that's what we ran into here. But the nice part about 4, number 1, the vertex, because we have no bx term, b is 0, so the vertex is 0, comma, whatever, which makes it the y-intercept, which means that vertex form is the same as standard form. Now, if you wanted to write x minus 0 or x plus 0 inside, right, for that x minus h, that's okay, but you don't have to. Saying x plus 0 or x minus 0 doesn't change x, so might as well make it as simple as you like. And because there's only one x in this whole equation, you can just solve for it directly, right? You can just jump in and go for it. Now, if you wanted to, you could factor out the negative 5, right? Because the first kind of factoring that we always look for when we're factoring is the greatest common factor. There's a -5 there, sure. But then that's the difference of two things, but they're not both perfect squares. Well, not perfect rational squares. It's irrational, but it is perfect. And you can factor it like that if you really wanted to. And you get your negative radical 3 and your positive radical 3. But seeing that might not be so easy. And so you always have just solving. It's a really easy way to do it. Okay, so F like that or F like this, and of course keep going. That's cool. Unless I tell you to round, don't. I saw a lot of 1.732s. Don't round. Okay, if I ask you to approximate or estimate or round, then you can do it. Otherwise, I always want the right answer, whatever that happens to be, without some decimal approximation that goes with it. So be careful, and if you wrote that, fix it. Right? I want you to have good work to look back at whenever we get ourselves to the point where we can see how we're doing. And the way that I think things are going to go, and I don't know, we'll see, but there's a lot in chapter 2. And it makes a lot more sense for me to cut it in half and do a first half of chapter 2 with quadratics and polynomials, and then a second half of chapter 2 with rationals when it comes to testing or quizzing or whatever we decide to do. Okay. What was the issue with 5 that you ran into right there? I'm gonna keep the rest of the answer hidden for a moment. What was the problem? Yeah. Now, does that mean that there aren't x-intercepts? No, but we do want to have a good sense for whether or not it's worth trying. And so I saw a few different ways of doing this, and I have two that I really like. Option number 1, if you couldn't factor, but you have it set equal to 0, how could you solve for those x-intercepts? How did you do it if you gave it a shot, or did you just get stuck and give up? I think a lot of us, if we gave it a shot, that's probably one way to do it. There's another way that I really like, so I'm not going to show it to you just yet. But like the problem with this down here at the 4x squared minus plus 6x minus 1, because it's not factorable, we can't take x squared and x and break them apart and solve for them separately. And so quadratic formula takes care of that because it's just x equals, and it gives us a nice formula to use. Maybe we have some simplifying under the radical to do, right? You got the square root of 52 stuck in there, right? And you had to, all right, square root of 4 and square root of 13, and so 2 radical 13. You had to simplify that radical. There's another way to solve an equation that's identical to this one. It just isn't written like this. Like, is there a version of this that means the exact same thing, that only has one x in it? Yeah. Yeah. Instead of taking standard form and setting it equal to 0, here's two options for you. What if we took, so quadratic formula works great, but what if we took vertex form and set it equal to 0? Same exact equation, just written a little differently, right? We did either our completing the square, or we just wrote it with the vertex and with that leading coefficient. And then you solve for it directly. Add 13/4. Divide by 4. Now remember, if I'm dividing a fraction by 4, I can make the top 4 times smaller or the bottom 4 times bigger. Now, 4 didn't go evenly into 13, so it makes sense for me to make the denominator 4 times bigger. But then, like, we still just have one x in the problem, so I can just solve for it. Take the square root of both sides. Right, so add 13/4, divide by 4, take the square root of both sides. When you take the square root and the square root cancel each other out, and we get to here, we have the plus or minus because we're taking an even root. But when you take the square root of a fraction, that is the fraction of individual square roots, right? Square root of the top and square root of the bottom. Well, the square root of 13 is just the square root of 13, nothing much we can do there, but the square root of 16 is 4. And it's already rationalized. I don't have to rationalize the denominator here. And then I just take this 3/4 and slide it over. And I'm done. And what do I get? The exact same answer. Now, some of us might have potentially stopped here, or it's possible you get to here, -6 plus or minus 2 root 13 over 8, and you just simplified kind of the 6 and the 2 and you did -3 plus or minus the square root of 13 over 4. Negative in front of that 3. And that's cool too. But one thing that I want you to start getting in the habit of, because when we get to 2.4, we get to complex numbers, we're going to have to break these apart. I want you to get in the habit of breaking apart the real part that's rational and the real part that's irrational. Now, and here's how we do it. What's 1/5 plus 2/5? Same denominator, right? Now, the step that we don't bother writing is this one, 1 plus 2 over 5. And if I can go this way and put fractions together, I can go this way and break them apart. And that's what's happening from here. Two things being added or subtracted on top, all over a single denominator. I'm going to break them apart over that same denominator, -3 plus or minus the square root of 13 over 4. Okay, so if you haven't done that, start getting in the habit of breaking things apart when you deal with either quadratic formula or, I mean, vertex formula is going to do that part for you, which I really like. And sometimes one's easier than the other, but you don't really know until you get into it. So you actually drop it into the quadratic formula and see what you get. Or you try vertex form and you see if it's simpler or not. So I don't have one way that I love more than the other. If I had to choose between one, I'm going to choose vertex form. Why? Because look at question, like part E of this question. You already did it. You already did the work to get you there. Quadratic formula is something I have to memorize. Remember, plug in right, simplify my square roots correctly, and then break them apart. Right? So there's a lot of stuff that you might, I don't know, make a mistake that you don't want to lose like silly points on, I forgot a negative, or I didn't simplify my radical because I didn't notice that factor of 9 that was in common, whatever, right? So if I had to pick one, I'd go option 2. Not always going to be easier, but most of the work is done for me, which I really like. Is that cool? So pick whichever one you want. I'm not going to say use quadratic formula, use vertex form. I'm just going to say find the x-intercepts however you want. Do you know how to tell what kind of x-intercepts you're going to get? Do you know how to determine, and you can write this down if you might, I think you might have seen it last time, determine what's called the nature of the roots. Like how to tell if it's going to be rational, like nice, irrational, like this one, or imaginary. Like just, I mean, I'll slide back up to right there because that's where things kind of get started. Do you know what makes the difference between nice stuff like numbers 1, 2, and 3, not so nice stuff like 4 and 5, or the stuff that we'll see in 2.4 that I'm guessing you did, right, with I, right, a plus bi, you saw it square root of -1. Okay. Do you know how to tell the difference without actually doing all of the work, but just picking on one little piece that makes rational numbers or irrational or imaginary? Like what part of this quadratic formula is going to make the difference between rational, irrational, or imaginary? Yeah, whatever's under here, right? That kind of takes control. If b squared minus 4ac is not a perfect square, it's got to be irrational because we end up with square root of 13, a square root of 7, a square root of 2, or square root of 101, or whatever it is. B squared minus 4ac runs the show. And that has a name. Do you know what that name of that? Just that part underneath the square root. No? Okay. The discriminant. Have you heard of the discriminant before? It helps you discriminate, not in a bad way, but to tell the difference between different types of roots. And if we've got a really nice perfect square, it's going to be rational. Now, if it was a perfect square, that means it was factorable from the beginning. All right, we get nice answers, we can go back and we can factor it for sure. And you can just check that, especially with really, really large numbers. Maybe I just want to drop it into the discriminant and not even take the square root, but just look at what happens with b squared minus 4ac and see what we get. Now, we might get, how should I say this? 1 x-intercept, or we might get 2. Which perfect square could I put right here that when I take the square root of that, negative b plus that number and negative b minus that same number gives me the same result? What's the only number that I can add and subtract and nothing changes? 0. If b squared minus 4ac is 0, it's the only time you're ever going to get 1 x-intercept. And it's going to be your vertex. No, it's going to come down. It's just going to hit the x-axis and it's going to take back off, or it's going to go this way. Either way. Okay. 2 x-intercepts. We're looking for something greater than 0. So equal to 0 or greater than 0. But it's got to be a perfect square. Okay. If it's irrational, it's still greater than 0, but it's just an imperfect square. I might have made up that prefix. I mean, I know it means not a perfect square, but I don't know. A perfect square, unperfect square, imperfect square. I think it's imperfect, right? You can be perfect, you can be imperfect, right? We're imperfect people. So I'm going to say it's an imperfect square. What's going to make it imaginary? What's underneath that square root? If I want it to give me an I back, negative. Cool. So real nice to be able to look at a quadratic and know, should I even bother factoring? Well, let me just check b squared minus 4ac and see what I get. Should I even go through the quadratic formula or try vertex form if it's going to be imaginary and I'm trying to graph this thing, right? Whatever the case may be. Cool. All right. So I just wanted to talk to you about that. All right. Let's look at the classwork from yesterday, because numbers 1 and 2 got us into stuff like this. But then I looked also at some indifference of cubes from Friday. And so if you have questions about that, and folks at home, if you want to start paying attention now would be a good time to do that. Where am I? I think I'm still in my drive, right? Yeah, okay. Now you can check your work from yesterday. Now, and I did it both ways through the x-intercept. I did quadratic formula and I did vertex form. Come on, zoom a little bit. There we go. And you can just pick one or the other. The left side or the right side doesn't matter, but you see that I get myself to that point where I'm breaking apart the real piece and the rational piece and the irrational. We're not going to get to complex stuff with imaginary numbers until 2.4. And so that'll be October sometime. But take a look, see how you did. Make any changes that you need to, especially with the way that the answer is represented. Of course, I'm going to accept this as the final answer because it's real. But the moment it's moment it's imaginary, we have to break it apart, a plus bi. But there's no I here, so we're good. So this one's fine, but this one's better. And I'm always going to get to that nice finished version when I use vertex form, which I really like. Let me make sure. Everybody at home. Sorry, 1 second. So I make sure I'm still presenting. Okay, cool. Decimals are okay for your vertex and for vertex form, but you know what? Trying to take the square root of whatever 17/16 is as a decimal, I can't simplify that all that well. But taking the square root as a fraction, to square to the top, square to the bottom, and I can simplify that denominator, which makes it so nice. So every chance I get, I'm going to use fractions. All the time, all the time, all the time. I love them, love them, love them, because I can do way more with them than I can with decimals. Okay, number 2. This one threw a little something at us when we used the vertex form, which is over here on the right. When you take the square root of a fraction, and you take the fraction of the top, and the square root of the top, the square root of the bottom, well, I had to take the square root of 2 in the denominator, and that's just the square root of 2. And so I had to rationalize that denominator. Right? Square root of 1/2 is the square root of 1 over the square root of 2, which is 1 over the square root of 2. But then I have to multiply top and bottom by that square root, so my denominator is rationalized. With quadratic formula, we don't have to do that. Which is why one is not necessarily better than the other. But I did have to simplify the square root of 32. Right? Square root of 16, square root of 2, so 4 root 2. The negative gets absorbed back into the plus or minus. So this negative right here gets absorbed back into here because plus a negative is subtraction, and minus a negative is addition. So you can nicely let that disappear kind of into the abyss. You don't have to flip it and put minus plus. You can if you want to get real fancy, like we do in the formula for sum and difference of perfect cubes. But even though this one wasn't factorable, it still had a nice vertex, which was cool. -1/2, 2. Questions on those first two? If you had to make a choice, you only got to do one or the other. How many of you, now that you know vertex form, would still choose quadratic formula? Sweet. How many of you would use vertex form? Options. Good. Use them. Whichever one you like, I'm cool with it. All right. Hopefully this clicked on Friday and you're able to make pretty good headway into factoring these kind of problems. Okay. A cubed plus or minus b cubed. Whatever they are. You can see how I wrote the formula up at the top there. You need to give yourself that base for this to work. So when it says a cubed plus b cubed or a cubed minus b cubed, it's pretty easy to just jump right in and choose my options, right? A, b, a squared, a, b, b squared. A, b, a squared, a, b, b squared. But the signs spell out soap. Same, opposite, always positive. Okay? And so what you see me do for stuff like 5, 6, 7, and so on, personally, I'm going to rewrite it with the base. It just makes it a lot easier for me to then just drop in those terms in here rather than having to always constantly go back and say, okay, 2 is the cube root of 8 or 4 is the cube root of 64. Especially when things get a little bit tougher and you've got leading coefficients. And certainly when we get to 8. And 8 was the one that probably gave you the most trouble if you had any. Because remember, the first kind of factoring we always have to do is greatest common factor. And so if you didn't notice that there was a GCF in there of 2x squared, you won't be able to factor that. But the moment that GCF comes out, what's left inside might have more going on. Maybe it's a difference of perfect squares. Maybe it's sum and difference of perfect cubes. Maybe it's a quadratic trinomial that you didn't notice was quadratic because you had an x or an x squared or an x to the 10th in there or whatever. But the moment you pull out that GCF, it gives you more options in how to factor. And this stuff is going to come in really nice when we get to polynomials and rationals. More rationals than anything, because I'm going to guess you did adding, subtracting, multiplying, and dividing rational expressions last year, where you had to either, when you multiplied or divided, you had to factor everything and then divide stuff away. Or when you added and subtracted, you had to create common denominators to be able to add these long, crazy rational expressions, right? That stuff comes in really, really nicely with stuff like this when we look at rational functions and the numerator is the difference of perfect cubes, or the denominator is, or whatever the case may be. Cool? Questions? So tomorrow you're home, unless you're a senior and you're taking your SAT. No? Anybody in here? Senior? There she is. So good luck. You're going to be awesome. I will have some practice for you, but nothing live tomorrow. Nothing live. I will be proctoring all day long. So we'll have some stuff like this just to make sure you're feeling good, but I want to get into 2.2. If you're ready, let's do this thing. So let's go. Here we go. 2.2. Polynomials of higher degree. Okay. So I'm just going to show you around kind of the basics of polynomial functions. But all you have to do is write the title right now. Don't write any of that stuff that's showing up right there, okay? Because all of that is stuff we already know. We have constant graphs, linear graphs, and we have parabolas. We've got our quadratics. But anything higher than that, any degree higher than 2, makes it a bunch more difficult to graph by hand. And so we're not going to graph them. We're just going to sketch them. We're going to look at some of the basics on what makes one polynomial different than another, and figure out what is that bare minimum for me, for you, to feel like, okay, what I've done is enough. If I'm going to sketch this polynomial graph, how can I know that I'm good to go? Okay, so let's do this. Okay, when you look at polynomial graphs, you're going to like them. Why? Because the graph on the left is a polynomial. They are continuous. From one end to the other, now there should be, I'm going to use the mouse so you can see it, there should be an arrow right there, and there should be an arrow right there. The textbook does not do a great job at drawing in the fact that these graphs keep going. So if you are sketching that, if you are writing that down somewhere, and you're saying the polynomial functions are continuous, and you want to draw yourself a little sketch, make sure that you put arrows on both ends. These graphs are always, 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 always going to have a domain that is all real numbers. Now, whether they both go in the same direction, those arrows, or like this one, they go in opposite directions, that depends on what kind of function we're looking at. But the kind of graphs that are on the right there, the functions that have that break in them, that have that one point where things end and then it kind of picks up somewhere else, those are not polynomials. We're not going to have breaks. We're not going to have gaps. We're not going to have holes. We're not going to have asymptotes in any of these graphs that we deal with here in the first half of chapter 2 with polynomials. Okay, and folks at home, if you have questions, just unmute yourself and give me a shout, and I will happily talk about it. Okay, polynomials, continuous. Love them, love them, love them. Makes it so much easier to deal with. Here's the other thing about polynomial graphs that we really like. They're smooth. They're round. They have these nice, gentle turns to them, so that when we connect all of the important points along the way, we can do it in a manner that's kind of, I don't know, it's like artistic in a way. Like there's nice, gentle turns. We don't have things like absolute value, where it takes that sharp turn and things drastically change in terms of like the slope. I mean, you're looking at absolute value, right? That's a piecewise function of two linear graphs, one with a positive slope, one with a negative slope, and it takes that sharp turn somewhere. Those are not polynomials, which is awesome. Awesome, awesome. We like the ones on the left, not so much the ones on the right. Okay, let's jump into this. Let me take attendance while this thing's getting loaded. 8, 10. Okay. How many should there be? There should be 12. Jaden, Rachel. 4, 8, 10. Who am I missing? Give me a shout. Let me know you're here. Jaden, Rachel. There's one. Megan, Logan, Zyla, Morgan, Blake, Megan, Alexa, Emma, Jansen, Colin. All right. Here's what I want to be able to do next. I want to get a sense for where those arrows are going to be pointing. So what I'm going to do is I'm going to jump to my calculator, and I'm going to give you a couple graphs to look at, and we'll see what we notice. And you don't have to write these down yet, but I do want to just take a look. At these 5 graphs. Now, we're not going to look at all of them at once, So I don't know if you remember, but I can go to these equal signs and I can turn them off by just pressing enter. 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 Okay. Take a look at these two. X squared and negative x to the fourth. There's x squared. There's negative x to the fourth. Let's zoom in a little bit. Okay. X squared and negative x to the fourth. What do you notice about their arrows? What direction are those arrows pointing? In the same direction or opposite directions? Same direction. But what makes the blue one go up and the black one go down? Negative x to the fourth is the black one, and positive x squared is the blue one. What changes the direction that those arrows are going? The negative, yeah. And so if I were to type in something like these two, negative x to the sixth versus positive x to the sixth, which one is going to be pointing up, the green one or the orange one? Right, positive leading coefficient should point me going up in that direction. But how do you know that it's going to be pointing both up or both down? Can you tell by some other piece of this? X squared did it, negative x to the fourth did it, negative x to the sixth versus positive x to the sixth. What about it? Even. If your exponent is even, arrows point in the same direction. So what do you think is going to happen if I get rid of all those? Gone, gone. And we look at exponents that are odd. What direction are those arrows going to be pointing? Opposite direction. Odd, opposite, odd, opposite, odd, opposite. If your exponent is odd, arrows pointing opposite direction. But when x squared or x to the fourth had a positive leading coefficient, they both went up. We've got x to the third and x to the fifth here. Positive leading coefficient, right? So I had this, and now we have this, x squared and x to the third. Which arrow, which side of this graph is the one that heads in the positive direction? The left side or the right side? You look at both of those graphs, and they're both positive, right? They have positive orientation. Which side of the graph is the one that's pointing in that positive direction? The right side. And that's the only one that we can really trust from the leading coefficient. Okay, so there's really two parts to this, right? What kind of exponent do I have? Is it even or odd? What is it's called the parity. Even versus odd. What is the parity of my degree? And what is the sign of my leading coefficient? Those are the two things that are going to take control. Okay? And so here's an easy way to see that. And this is, I'm telling you, this is right out of the book. They do a pretty good job, so I like it. Scroll, 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 scroll. There's two parts to it, right? The leading coefficient and the degree. And there's our function, right? A sub n, x to the n plus blah, 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 all the way down to a sub 0. If your degree is odd, your arrows are pointing in different directions. And it's the sign of the leading coefficient that makes the difference as to which way things are going. And so usually what I like to say when I try to figure out, and so this whole thing is called end behavior. When we talk about which direction our arrows are pointing, when we think about graphing polynomials, a great place to start, which is kind of weird, is the end. Now, we'll look at one thing probably before that so we know where to put those arrows. But it's kind of a combination of two things. So option number one, degree. That's not how you spell degree. Degree. Option number two, the sign of, and I'm just going to say, a sub n. Right? Your leading coefficient. You've got two options for degree. It's either even or it's odd. Okay? If it's even, your arrows point in the same direction. If it's odd, your arrows point in the opposite direction.
Mr. Rosengren?
Uh-huh.
If you're writing on the board, we can't see it.
Oh, it's coming. You're coming with me, I promise. Yeah. I know. How's that? Can you see that? Let me angle it up just a little bit. There we go. Okay. So, end behavior, your arrows. You got two things that we're going to look at. Your degree, if it's even, or if it's odd. Odd, opposite, odd, opposite. Okay. The sign of your leading coefficient. A sub n could be positive, or A sub n could be negative. If it's positive, if your leading coefficient is positive, then your right arrow is pointing up. If your leading coefficient is negative, your right side arrow is pointing down. I don't know the arrow on the left without looking at the degree and the sign at the same time. So I have to kind of consider both options. Right? If I want to figure out my end behavior, if I want to know where these arrows are going to be pointing, because what we're trying to do is sketch these. I want to get a sense for how can I graph a pretty decent looking version of this. Now, I can't do it great because I don't know calculus yet, so I can't figure out where these turns happen without calculus. But what I can do is decide on the end behavior. Good. Have you seen that before? Talked about polynomial graphs? Okay. So this should be generally a pretty easy way to get things started. So let's see what you got. Let's see what you can do. I just want to know end behavior of the following graph. Let me get back to present mode here. Back to this. Okay, let's go here. Okay, take a look in A and B and make a choice. Describe the right hand and left hand behavior. So just those arrows, the end behavior of this graph. Describe which way it's going. And you can say it as simply as up, up, down, up, down, or down, down. Or you can even just draw arrows. You can just say, there's my answer. There's my answer. There's my answer. There's my answer. You've got 4 choices on how to do that. Because we can't fill in any of the space in between just yet. And with each one of your arrows, they have to be pointing out. The left arrow needs to be pointing left. Not just down or up, but also out to the left. The right arrow should be pointing not just down or up, but also out. Right? Because these graphs go on forever. They're continuous and they're infinite. Polynomial graphs, I can plug in any x I want and get a value back. So the domain of both of these, they are both infinite. So take a look. Tell me what you get. First one, A. What is the end behavior of that graph? Both up. How'd you know? Even degree? Positive leading coefficient. There it is. Up, up. Okay, what about B? What is the end behavior of x to the 5th minus x? Down on the left up on the right, right? Odd degree, so they're opposite, and I can only decide the right arrow from the leading coefficient. Because it's a leading coefficient that's positive, I know I'm up on the right, and because the degree is odd, I'm going down on the left. Okay, what about that one? What is the leading coefficient test? And really, it's just more than that. It's not just leading coefficient, but it's the degree and the leading coefficient that helps me describe. They call it the right hand and left hand behavior, right hand and left hand behavior. That's 6 words. I'm going to call it end behavior. 2 words. Describe the end behavior of this function. And when you say it out loud, you have to say words like up, down, but you can just go like this. Up, down, 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 up, up, or down, up. Up on the left, down on the right. Odd degree, opposite. Leading coefficient negative, so my right side is going down. Good? Okay. The only other major points that we can deal with in between are the x-intercepts and the y-intercept somewhere, right? But the x-intercepts are much more difficult for us to figure out. Remember, actually, let me do this, backing out for a quick second, that when a function is written like this, right there in the middle, f of x as a long polynomial function written in standard form, what's the y-intercept of this function, no matter what all of that is? Where is the point when x is 0? What's the y value you get back? Always, no matter what. That last term. Because 0 plus 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 0, however many there are, plus the only term that doesn't have an x in it. Okay? So your y-intercept will always be your constant at the end of your function. Okay, so that one's not all that bad. But when we try to figure out something like these, the zeros, also known as the x-intercepts, the roots, we have a little bit more work ahead of us to do that. And if this was quadratic, it'd be fine. If this was linear, piece of cake. If it was constant, no problem. But this is a polynomial of higher degree. And so if we wanted to sketch this out, okay, number one, where's the y-intercept? What is the constant being added at the end of that function? That's the coefficient of x. So that's a sub 1. A sub 1 is negative 2. What's after that? Plus 0. So your y-intercept is the origin. And knowing that ahead of time makes things a whole bunch easier, because if your y-intercept is the origin, so is one of your x-intercepts. And so if we are looking, and folks at home, I'm bringing you over here in a second. If we are looking to solve for the x-intercepts, well, we have a couple things we can do first. We can figure out what the y-intercept is too. And we know for sure that that's just going to be 0. Okay, and now the glare sucks. I'm going to talk this out loud as much as I can for the folks at home. Okay. So I know, and I'm going to grab the black, purple. I know that the y-intercept happens at 0, 0. Ooh, the purple is nice. Y-intercept. Let's talk about the end behavior. X cubed minus x squared minus 2x is our function. What's the degree of that function? The largest coefficient, right? Or the largest exponent, whatever that is. In this case, 3. So odd is my degree. So the degree is odd. So odd, opposite, I'm going in opposite direction. Leading coefficient's positive. So it should look like this, right? Down on the left and up on the right, and you can just do that. That's fine. Let's find some x-intercepts. What should we set this thing equal to solve for the x-intercepts? Always, right? Just like we do with quadratics, we're always going to set our polynomial function equal to 0. Okay, how do we get that thing solved? How are we going to get ourselves down to here? X equals some set of nice zeros. Roots, x-intercepts, whatever you want to call it. Solutions to this equation. Factor. And we're going to do a lot of different kinds of factoring to get ourselves to find these x-intercepts as easy as we possibly can. What's the first kind of factoring you should always do? Always. If you don't pull out a GCF first, you're going to be out of luck. A lot of the things that we do. And so what is x cubed, negative x squared, and negative 2x? What do they have in common? Pull it up. GCF first. X cubed minus x squared minus 2x. I pull out the x. Okay, so I have one of those that are gone, one of those that are gone, and the one that was with that negative 2, that one's gone as well. So x, parentheses, x squared minus x minus 2. Now what? Because I still have different powers of x here. And if a factor that I have different degree powers of x, I have to keep going. I have to keep factoring, if I can. And if I can't factor, it better be quadratic so I can use a quadratic formula. It's the only backup that we have when we get stuck and we have different degree powers. And so there's different things that we're going to be looking for. And it's not that anything from here is like there's a great order to go in. It just depends on what you've got. But first has to be GCF. Guaranteed. Got to have GCF first. But from here, what do we have left inside? I want to deal with what's inside here. I want to see if there's more that I could do. How would you describe what's left inside? What kind of function? Just the x squared minus x minus 2 part. What is that? Quadratic. How many terms are there on the inside? So what do we call that? Trinomial. Okay, and that's where we get into here, right? Two numbers that add to b multiplied by a times c, and you do your quadratic factor. And that's just one of the options that we could run into. And so I do it. I say, okay, what two numbers add to -1 and multiply to -2? So much easier to see it when it's written down. Adding to -1, multiplying to -2. And because my leading coefficient is just 1, I can just factor it. All right, so we have kind of two options here, right? A could be equal to 1, or A could be not equal to 1. And that makes a difference on how much work it's going to take to get that thing factored. But either way, you've got this ax squared plus bx plus c, and I just factor. Okay, how many different factors do we have here? How many unique factors are there? So how many x-intercepts are we going to have? Yeah, right? So there's really all three of these cases that we want to look at, where the first factor is 0, where the second factor is 0, and where the third factor is 0. And I just want to solve for x for each. And because each of these terms are linear, or really there's just one degree x in there. I don't care if it's x or x squared or x to the third or x to the 10th. I can solve any of those as long as there's only one of them. Then we're good to go. So if x equals 0, what does x equal? Right. And if this was 2x or 5x or 10x or 3x to the 4th, 0. You have a monomial term, we just have 0. And 2 and -1. And if you want to just circle those, that's cool. If you want to write them down from left to write as a solution set, you can do that as well. Okay, and now we try to sketch it. And when I say sketch, I mean sketch. I mean, I don't need to break out the ruler. I don't have to break out any kind of straight edge, any way to do this. Oh man, no way. What a bummer. So lame. All right, we'll pick this up on Thursday then. All I would have done is plotted the x-intercepts, put some arrows on the ends, and then disconnected it. 0, -1, 2. On the outsides, I do my down this way and up that way. Up, down, and up. And that's what it looks like. But we'll pick it up on Thursday. Check Canvas for your work for tomorrow to help get you there. Thanks, everybody. See ya. Folks at home, any questions? If you're good, you are good. Peace and love. I will see you back here, same time, same place, on Thursday to live stream that lesson. Thanks for being at home. I appreciate you guys. Adios. Stop the recording.